In this course, in addition to the xy coordinate, we are going to learn two more coordinates to describe the motion of a particle in plane. One of them is called path coordinate or normal tangential coordinate, which is quite useful in a lot of different types of problems. What is this coordinates? If you look at a particle which is moving on a path in plane, this is the path of movement. This particle is moving on this path. If you look at this particle, you're going to see the velocity of the particle is always tangent to this path, right? Because if it's not tangent to the path, it means it's going to be out of this path, which is not possible because this is the path of movement, right? So the velocity of the particle is going to be just in this direction, which is tangent to the path. At any other points, again, the velocity is going to be tangent to the path of movement in that point. We are going to call this tangent direction, we are going to show it with the unit vector of ET, tangential coordinate. And also perpendicular to this coordinate toward the center of this curvature, we are going to call it normal direction and show it with E hat N. This is our tangential coordinate or tangential unit vector, and this is the normal unit vector, tangential, normal. A moment later, when the particle is here, the tangential unit vector is going to be tangent to the curve, so it's going to be in a different direction, and also the normal direction is going to be a different one. So ET and EN, they are changing at any time. But at any time, we know the velocity is going to be just in the tangential direction. So we can write it as the magnitude of the velocity times the direction of the velocity, which is E hat T. So this is the velocity. And V, without the vector sign, is the speed or the magnitude of the velocity. Okay? And to find the acceleration, we can take a derivative of this to find the acceleration. Derivative of velocity is acceleration. That's the definition of acceleration. So we need to take a derivative of all of these. So d dt of v e hat t. And we have two variables here that we need to take derivative of them. And none of them is constant. Speed can change. And also this unit vector E hat T is changing with time. So it is not constant. We have to take a derivative with respect to time from this variable as well. Using chain rule, this derivative is equal to a derivative of velocity, which is V dot times ET plus V times change or the rate of change of ET or ET dot, right? This is derivative of ET, how this ET is changing with time. I'm not going to show or prove this for you, but the proof is quite simple and you can see it in the book. If this angle, the angle of the velocity from the horizontal direction, if I call it theta, then we can show ET hat dot is equal to theta dot times En. In general, the time derivative of any unit vector is going to be the angular velocity of it, theta dot of it, times the rotation of this unit vector 90 degree in the direction of the theta, which is En here, right? And in the same way, we can prove En dot, the time derivative of this unit vector, is going to be theta dot times the rotation of this by 90 degree, which is going to be negative ET. So it's going to be negative theta dot times ET. So I'm not proving this for you, but you can see the proof in the book. So the acceleration is going to have two components. Let's write it again. Acceleration is equal to v dot in et direction plus v times et dot. So it's going to be v times theta dot times et. And the other thing which I'm going to give you an equation here, but I'm not going to prove it. And again, you can see the proving book. If you find the radius of curvature of this path at this point, the radius of curvature means the radius of the biggest circle. You can tangent to the circle without crossing it, right? So if this is the biggest circle that you can tangent to this path at this point, the radius of it is going to be something which I'm going to call it rho. A moment later here, the radius of curvature can be totally different thing. Okay. If we have the radius of the curvature at this point, mathematically we can show velocity or speed is equal to radius of curvature times theta dot. So this is another equation without proof. And I'm going to put it here to simplify this equation and give you the final equations. So if I replace this here, if I replace theta dot with v divided by rho, I'm going to have acceleration is equal to v dot times et plus v times v divided by rho, or velocity squared divided by rho times et. This is a very important equation, and I'm going to explain why this is important. It shows when you have a particle which is moving in plane, acceleration is going to have two components. One of them is going to be tangent to the path of movement, which is v dot, and v dot means change in the speed. So if your particle, the speed of the particle is changing, you are going to have one acceleration there, and that acceleration is going to be just in the tangential direction. The other component of the acceleration is in the normal direction. Oh, I made a mistake here. So this is En. The other component of the acceleration is just in the normal direction, and the magnitude of it is velocity squared divided by the radius of curvature. What's the meaning of this? It means if you have a particle in plane which is moving without changing the speed of it, let's say the speed is constant, it is like 10 meters per second all the time, but it is moving around and turning around. That particle, even with the constant speed, is going to have acceleration because it is changing the direction of it. And the acceleration of that particle is going to be just in the normal direction. And the magnitude of the acceleration is going to be velocity squared divided by rho. So in general, we have two accelerations. One of them acceleration in the tangential direction, which we show it with et, which the magnitude of it is v dot, change in the speed. And the other component of the acceleration is in the normal direction, and we show it with an, and the magnitude of that acceleration is velocity squared divided by rho. For example, if you have a particle which is moving on a circle, which a lot of times actually we have this case in your book. Let's say we have this circle with the radius of r, and you have a particle which is moving here with the speed of v, and v can change, but all the time it is moving on this circle. At any time, this particle is going to have two accelerations, or in general we can say acceleration of it has two components, in the tangential direction and also in the normal direction. The normal direction is going to be this, toward the center, and the tangential direction is going to be this. Acceleration in the tangential direction for this particle is v dot, and acceleration in the normal direction is going to be equal to velocity squared divided by rho, the radius of curvature, which for a circle the radius of the curvature is r all the time. Okay? Or sometimes people write this, actually use this equation. velocity is equal to radius of curvature times theta dot, and theta here is, we can say it's equal to this. If you replace v with r theta dot, we are going to have r times theta dot squared. So both of these equations are correct for the normal acceleration for a movement on the circle.